Hello there, my name's John Bone and I'll be your guide to this module on organising, visualising and describing data. So let's turn our attention to our first learning outcome. And our first learning outcome asks us to identify and compare different types of data. And the different types we've got are numerical versus categorical, time series versus cross-sectional, structured versus unstructured. So what we need to know here is the definition of each type of data and the differences between each type of data. So let's start off with our numerical data. Now, the first point on the slide that is very important is that it is quantitative data. In other words, it has some numerical value. It can either be counted or it can be measured. Now, our quantitative numerical data is either discrete or continuous. Discrete data, notice, are in countable units. In other words, there's a finite number of outcomes. So, for example, if I asked you how many days did it rain last week, you would be able to tell me a countable number. It's either going to be between 0 if it didn't rain at all, or 7 if it rained every single day. Okay, and it could take a value anywhere between there. It could take a value of 0, 1, 2, 3, 4, 5, 6, or 7, the number of days in a week. But the key point with discrete data is there is a finite number of outcomes. Now, when we turn our attention to continuous data, our continuous data takes on an infinite potential amount of outcomes. So, for example, if I asked you how much rain was there last week, now, if you're measuring rain, you could measure the rainfall to as many decimal places as you want. And that means you potentially have an infinite number of outcomes. So the key point is the data can take on fractional values. In other words, we can measure the observations to as many decimal places as we want. And as a result, essentially there is an infinite number of outcomes. So if I ask you for the rainfall last week, you can measure it to as many decimal points as you want. And therefore there's an infinite number of outcomes for the rainfall next week. Another example of discrete versus continuous. Let's take shoes. Now, if I ask you what shoe size you are, then that's probably a discrete variable because, again, only a finite number of shoe sizes are actually manufactured. So therefore, there's countable units here. But if I ask you your foot size, then the data is most likely to be continuous because I can measure your foot size to as many decimal places as I want. And then again, therefore, there is potentially an infinite number of outcomes. Now, of course, in the CFA, often we're looking at stock returns and stock prices. And of course, you can measure the stock return to as many decimal places as you want. So stock returns often, therefore, are continuous data. Now, key point with quantitative data, numerical data, is you can perform mathematical operations on numerical data. In other words, we can work out the mean, the mode, the median. We can work out the standard deviation of observations around the mean. Okay, so we can perform mathematical operations on numerical data. Now that contrasts with our categorical data. Now, categorical data is qualitative data. Okay, so it has some quality, but it's not numerical. Now, the issue is you cannot perform mathematical operations on categorical data. So really with our categorical data, what we're trying to do is come up with labels for grouping or classifying data by some characteristic. Now, nominal data just means our labels have no logical ordering. So for example, let's imagine we've got an object and we have to allocate it to animal, vegetable, or mineral. Okay, there's no ordering. We're not saying an animal is better than a mineral, is better than a vegetable in any way, shape, or form. So there's no logical ordering with those labels. Likewise, if you think about stock market classifications, so we might have energy companies, defense companies, pharmaceutical companies, healthcare, etc. Again, these are labels that describe the type of company activities, but they don't have any logical ordering. We're not saying an energy company is better than a defense company, is better than a pharmaceutical company. So key point with your nominal data, there is no order to the labels. Now let's contrast that with ordinal data, and I always remember this as ordinal starts with ORD and so does order. This time the labels are ordered. So for example, let's imagine we're looking at companies' market capitalizations and we're ranking them as small cap firms, mid cap firms or large cap firms. Now, if an observation is allocated to a large cap label, then we can say, well, it must have a market capitalization that is bigger than mid cap. Mid cap firms must have market capitalizations bigger than small cap. So now with ordinal data, the order does matter. Now, again, you probably come across ordinal data quite regularly. Think about satisfaction surveys. You often find these in shops, for example, at the end of the place where you pay for your goods. And it might have a button that is a happy face. It might have a button that is a kind of intermediate face. And it might have a button that is a sad face. And it asks you to press the button to grade or label the service that you've received. Now, notice, of course, there is an order here. If I press the smiley face button, then, of course, the company will deem that I am more satisfied with their service than if I press the other two buttons. And, of course, if I press the sad face button, then the company is going to determine that I am less satisfied with the service that I've got. So here, the order is in terms of satisfaction of the survey of the service I've received. Let's imagine you're drinking a cup of coffee and I tell you, or I ask you to rank your coffee as very hot, hot, warm, cold, or very cold. Again, ordinal data. If you put your coffee into, let's say, hot, then I know that you find that coffee hotter than warm, cold, or very cold, but less hot than very hot. But of course, what I can't say is a very hot coffee is twice as hot as a cold coffee or 4 times as hot. So I can't really distinguish, I can distinguish the order of the labels, but not the differences between labels. Okay, let's turn our attention to time series and cross-sectional data. Let's start off with time series data. Time series data, we are collecting data at equal time intervals over a period of time. Okay. So in other words, maybe I'm looking at the monthly stock return. Okay, so I'm looking at the price at the end of the period divided by the price at the beginning of the period. So maybe price at end over price at start of the month minus 1 to convert it into a percentage. Okay, so I'm looking at the stock return for a company and I'm recording it monthly. Because I'm collecting that data monthly, then I am looking at time series data. Now that contrasts with cross-sectional data. Typically with my time series data, I'm looking at a single company, but I'm looking at its returns over a period of time. With cross-sectional data, I might be looking at multiple companies, okay, but I'm interested in their returns at a single point in time. So there's our key wording there. It's at a single point in time. So notice I've taken a sample of utility companies here. Let's say I've got 10 utility companies and I'm looking at their 2023 return, annual return. So all of those companies, I'm looking at their data at a single point of return at the end of 2023. So time series data collected over a period of time, cross-sectional data, multiple companies in our example, or multiple observations, but all at a single point in time. Now the final is panel data, and this really is going to combine time series and cross-sectional data. So for example, to use our stock returns example, maybe I'm looking at a sample of utility companies, so I'm looking at my 10 utility companies, but I'm interested in their monthly returns over the period of 2023. So I've got 12 observations for each of the companies that I'm looking at. So cross-sectional, because I'm looking at multiple companies. Time series, because I'm looking at their returns in each month over that period. We then turn our attention to structured data and unstructured data. Now, our key with structured data is it's organized in a defined way. In other words, specific data is stored in a predetermined format. Think databases, think spreadsheets, think tables, in other words. The key that it is clearly defined and structured. So maybe I'm looking at GDP per country, where it's listed by country, and then I show GDP maybe over time, or employers by their birthdays, for example. So our structured data can be time series, it can be cross-sectional, or it can be panel data. The key, though, is it is organized in a defined, structured way. And as a result, we can do things like search the data and run analysis of the data. So we can apply quantitative techniques to our structured data. Now, unstructured data, its information in forms with no defined structure. Now, what does this actually mean? Well, it means that it is stored in its native format. Now, this contrasts very much with structured data. Structured data is highly organized, it's factual, it's to the point, it's quantitative. With our unstructured data, it really is none of those points. Yes, it may have some numerical data in there, but it may be mixed up with words, tables, all sorts of stuff. So we're thinking about things like emails, social media posts, videos, images, audio, sensor data, all of that kind of stuff. The idea is it's predominantly qualitative data, and therefore we must transform it into structured data before we analyze it. In other words, we need to be able to extract the numerical data from this qualitative unstructured data. Okay, and we're going to see that in fintech, in investment management, in the portfolio management topic area. Okay, so structured data, very much organized data in a defined way. Unstructured data, it's in its native format, reports, accounts, emails, Word documents, all sorts of different forms of media when we need to extract the data, okay? And that extracting the data is what we mean by transforming to structured data for analysis. Now, our next LOS here asks us to describe how data are organized for quantitative analysis, okay? So how do we organize the data before we start processing it numerically? Now, a one-dimensional array, key point here, single variable. So it could be a time series. So maybe we're looking at a company and we're looking at its stock price over the last 5 trading days, for example. So if you think about it in terms of a table, you've got one row, the stock price, and then or the stock name, and you've then got 5 columns for the stock price or the closing stock price at the end of each trading day. So one row, multiple columns. Now, a 2-dimensional array, key point is we've now got 2 variables. So maybe we're looking at multiple companies and their stock price over the last 5 trading days. So now we've got multiple rows. So we've got one row for each company and we've got 5 columns, one for each trading day. Okay, so notice, of course, once we start to getting into this, we're looking at data tables with multiple rows and multiple columns. So think about a table. Think about spreadsheet data, for example, being a 2-dimensional array very often. And the key point, 2 variables. In this case, we had the companies and we had the closing price on each of the 5 days. Or maybe we're looking at one company, okay, but we're looking at 2 variables. Maybe we're looking at closing stock price and we're looking at volume traded. In this case, we've got two rows, one for stock price and one for volume traded, and we've got our 5 columns for each day of the trading week. Okay, add more variables and then you're looking at multi-dimensional arrays. Now, our next LOS asks us to interpret frequency and related distributions. I'm going to talk briefly about this slide and then we're going to do it by looking at the example that you've got in your Schweser notes. So frequency distributions summarizes a large data set. Okay, so what we're going to try and do is take a large data set and summarize it so it's easier to understand. It's easier to see the big picture. And we do this by creating intervals. Now, key point is these intervals will not overlap. What we're then going to do is take our data set and we're going to assign each observation into the intervals. Now, the absolute frequency is simply the number of observations that lie in each interval. Relative frequency, all we're going to do is convert the absolute frequency into a percentage. So it's the number of observations in the interval divided by the total number of all observations. 2 other measures we're going to look at here, cumulative absolute frequency. Now notice this is the sum of values less than the upper bound of each interval. So how many observations lie below the upper bound of an interval? And then the cumulative relative frequency, which is essentially the total percentage of observations less than the upper bound of each interval. Right, okay, let's do this with some data. Let's make it come to life with a bit of a numerical example. Okay, so here's the example that you've got in your Schweser study notes, and I'm looking at table A. I can see I've got the annual returns from Intelco Incorporated, and I've got 4 columns, each with 5 observations within them. So I've got 20 annual returns for Intel. Okay, but looking at the data, it's really difficult to tell, much about it because we're being overwhelmed by the number of data. I can see roughly by looking at it that some observations are positive, some observations are negative. So sometimes they had negative returns, sometimes they had positive returns. I can see maybe that, oh, look, the very biggest return was 40.4. And we could look for the lowest return. What's the lowest return? It looks like 28.6. So we can get some idea of a range here. But it's hard to understand how the data is really distributed. So what I've done is I've come up with 8 intervals. Now, the number of intervals you choose is rather subjective. Now, of course, the more intervals I choose, then the harder it is to see the big picture. But the fewer intervals I choose, the easier it is to see the big picture, but of course I'm losing fidelity. Okay, I'm losing the ability to see the minutiae, if you like. So we've come up with 8 non-overlapping intervals. So let's just take these intervals here. You can see they're non-overlapping. We've got less than 30% to greater or equal to 20%, less than 20%, greater or equal to 10%. So if we had a stock return of 20%, then of course it would apply to this column and not this column. So key point, they must be non-overlapping. You can't end up with an observation appearing in more than one interval. Okay, then we've just gone through with tallies. So the first observation, 10.4. So we go to 10.4 and put a mark there. Second observation, 22.5. Okay, so we make a mark there. Third observation, 11.1. We make a mark there, and so on. Now, the total number of dashes we make should be 20, equal to the number of data observations that we've got. All we're then going to do is turn our tallies into absolute frequency. Okay, and this just means counting the tallies. So there's actually only one observation that lies less than minus 20%, but greater or equal to minus 30%. There are 2 observations that lie less than minus 10%, but greater than or equal to minus 20. 3 observations that lie less than 0, but greater or equal to minus 10. 7 observations that lie less than 10%, but greater or equal to 0%. Now, we do this for all of our intervals, and straight away, we can now start to see some trends in our data. We can see that the most frequently recurring interval, or the most, if you like, the most observations that we've allocated to an interval are in the range less than 10, greater than or equal to 0. Okay, so in other words, 7 observations lay in the interval greater or equal to 0%, less than 10%. So we can start to get a feeling for this. Now, one of the other things we were talking about is cumulative absolute frequency. I'll just call it CAF, cumulative absolute frequency. Now, this is the number of observations that lie below the upper bound. So the first upper bound is less than minus 20%. And there's only one observation that lies there. The second interval has an upper bound of less than minus 10%. And you can see 2 observations lie in that interval. So what we're going to do is add these 2 numbers together and say, in total, 3 observations are less than minus 10%. And then we just keep on adding. So the next one takes the first 3 and adds them together. 1, 2, and 3. That gives us, of course, 6. So 6 observations lie below 0%. Add the 7. 13 observations lie below 10%. Add the 3. 16 observations lie below 20%. Add the 2. 18 observations lie below 30%. And then, of course, we get 19 lying below 40% and 20 lying below 50%. Okay, so that's our cumulative absolute frequency. The total number of observations lying below the upper interval. Okay. Now, next thing to talk about is our relative frequency. I'm going to call that RF, relative frequency here. And all we're going to do is take our absolute frequency and convert it into a percentage. So 1 out of 20 observations lie minus 30 to minus 20. So that's 1/20th, which is, of course, 5%. 2 observations lie between minus 10 and minus 20, so 2/20ths. So 10% of our observations, of course, 10% of our observations lie in that interval. And we just keep on going. So 3 observations lie in the interval 0 to minus 10. So that's going to be 15%. 7 observations, our highest frequency, lies less than 10 to greater or equal 0. And that's going to be 35%. Then we go back to 3 observations again, which is 15%. 2 observations in the next interval, which is 10%. And then 1, 5%. And 1 observation in this interval, which is 5%. Now, of course, if you add up your relative frequencies, you should get 100% or all of the observations. Now, again, this is nice and useful because we can now see that 35% of observations lie between or greater than equal to 0, but less than 10. We can see, for example, quickly by looking at this, that that 15% of observations are less than 0, but greater or equal to minus 10. Now, the next thing that we can do with our frequencies is we can work out the cumulative relative frequency. So CRF, cumulative relative frequency. Now, this is the proportion of observations lying below the upper bound of your interval. So first of all, less than minus 20%, well, 5% of observations lay below that bound. If we're interested in proportion of observations lying less than minus 10% or below, then we take our relative frequencies and we combine them and we get 15%. So we can now say 15% of observations have a return that is less than minus 10%. What proportion of observations have a return of less than 0%? Well, let's add the 15, so we're now running at 30%. 30% of all of our observations are negative, i.e. have a return that is less than 0%. And we could keep on going, so add the 35 to get 65%. So 65% of all observations are less than 10%. Add 15 to get, 80%. And I'm just going to keep on doing this, 90%, 95%, and 100%. So, of course, what we're saying is 100% of all observations are less than or equal to 50%. Let's have a look at those visually. So there's our relative frequencies that we were looking at. So there's our 5%, 15%. Sorry, it wasn't 15%, was it? It was 10%. 10%, 15%. Then our large one, which was 35%. Then we had, 15% again, then 10%, and then 5%. Okay, and again, of course, this is just a visual representation now of our data. And we can see, therefore, that the highest bar is the greatest relative frequency. And we can see that that is our interval 0% to 10%. And we can see that it's 35%. But it gives it a very easy visual representation. We can do the same things with our cumulative frequencies. So our cumulative frequencies, which were 5%, then went 15%, then went 30%, then went 65%, then 80%, then what was it after 80%? 90%, 95%, and 100%. Again, just giving us a nice graphical representation of the steps up. So you can see the steps, the incremental increases here. So you can see when I was looking at observations that were less than 0%, then I got 30%. If I change that to observations less than 10%, it jumps to 65%, which of course is a 35% increase. So nice visual data there. Now our next LOS asks us to interpret a contingency table. Now a contingency table is a two-dimensional array. Two-dimensional array. Okay, now remember, one-dimensional array has one variable, two-dimensional array has two variables. So it's displaying two variables, typically in a table format. Okay, now what we've got here in our data, and you'll see this example in the Schweser notes as well, is traffic accidents at highway intersections. And we've got 1, 2, 3, 4 traffic intersections, and we've got the days of the week. So we're only interested in working days in this particular example. Okay, so you've got two variables here. Okay, remember the rows are one variable and the columns represent your other variable, essentially. Now, variables can be nominal, okay, or ordinal. Now, ours are nominal in this case because we've got numerical formats here. Now, what we're seeing, therefore, is, let's just take this observation here. It's saying that were 5 traffic accidents on the Monday in Palace Street. Okay. Or we could say, by looking at this number here, there were 3 traffic accidents on Thursday on Front Street. Okay. Now, the data itself are joint frequencies. Okay, so the 5, the 3 that we circled there, these are joint frequency. It's not only telling us information about the day of the week, but it's also telling us data about the intersection as well. So when we circled that 3, it is the number of accidents on Front Street on a Thursday. So it is a joint frequencies. We've got 2 variables, accidents on Thursdays and the street there. Now these joint frequencies can be displayed as absolute numbers, and in this case we've got absolute numbers, the number of accidents. But what we could do is display them as relative numbers, i.e. percentages, okay, if we wanted. Okay, you can do that as well. We've also got something there called our marginal frequencies as well. Let's have a look at our marginal frequencies. There's a marginal frequency, and that marginal frequency is the number of accidents at Front Street. Okay, so in other words, over the 5 days of analysis, there were 25 accidents on Front Street, and that is referred to as a marginal frequency. We could also look at it for maybe Monday and say, well, there are 19 accidents in total on Monday. So that is the marginal frequency of accidents on a Monday. Okay, and notice, therefore, we've got 68 accidents in total. And we can use that, of course, to therefore work out relative frequencies. You know, you could be interested in what proportion of accidents occur on a Monday, in which case we could look at 19 divided by 68 and say, well, okay, 27.9% of all accidents occurred on a Monday. Now, useful thing, but looking at our marginal frequencies is immediately we can see things like the most dangerous street. Well, look at the totals, okay, and look at the total for Front Street. 25 accidents in total occurred on Front Street. Again, if you wanted to convert that into relative data from absolute data, 25 divided by 68, and we're saying 36.7% of all accidents occurred on Front Street. What is the most dangerous day of the week? Well, you can see Monday totals 19, and that is the highest marginal frequency of any day in the week. So Monday is the most dangerous day to drive on those highway intersections. Okay, so remember the table data itself are joint frequencies. They can be displayed in absolute terms, and that's what we've got here, number of accidents, or relative terms, i.e. converting them into a percentage. Let's have a look at a confusion matrix, which is our last part of this particular module. A confusion matrix is another form of contingency table. And again, we're going to use the example in Schweser for this. It's going to display predicted and actual occurrences of an event. So this is the key point. It shows you what you predicted against what actually occurred. Now we've got a total here of 1,000 events, and we're going to say label it as yes if we think an event occurs and no if we think that event doesn't occur. Now notice when we look at the predicted data, 662 times we thought the event would occur out of 1,000, and 338 we thought it wouldn't occur. Now again, these are absolute figures. You could convert them into relative. 662 divided by 1,000 is going to be 66.2%. So we thought the event would occur 66.2% of the time and failed to occur 33.8% of the time. Now notice then, if we look down our columns, we're looking at the actual. So actually, the event occurred 681 times out of 1,000 and didn't occur 319. So in other words, it occurred 68.1% of the time and didn't occur 31.9% of the time. Immediately, we can see the event actually occurred more frequently than we predicted. We predicted 662, or 66.2%, and actually it occurred 681%, so slightly higher. We can also start using these confusion matrices to understand when our predictions were wrong. So for example, if we start to look at this column here, we predicted, actually let me just make some lines come up, 47. So in other words, the model predicted the event would not occur. Okay, notice when we look across, we're in the no row, and that's our predicted. Okay, so we thought it wouldn't happen 47 times, when in fact it did happen because it's in the yes column. So the model predicted the event would not occur, but in fact it did. Likewise, we can look at our 28 here. Here, we predicted the event would occur. Again, notice we're in the row, okay, of predicted. So we predicted the event would occur, but in fact, in actuality, it didn't occur. So in other words, our model is incorrect here. It's either predicting the event won't occur, and it has, or it's predicting the event will occur, and it has not. Okay, so a lot of data in a confusion matrix.